Hello and welcome to this webinar series, Machine Learning Made Simple, brought to you by SIAM VIT. I am Saksham Arora, your host for today's session. And at this point, I hate to break it to you, but I'm just gonna wait for a minute or so that more audience may join in, and then we'll start this live session together. Alright, so I guess people might be adding up at this moment. So while we wait for them, I'll tell you a bit about SIAM. SIAM stands for Society for Industrial and Applied Mathematics. It is an international chapter with a population of more than 14,000 individuals across the globe. It has presence only in 5 colleges in the country, with VIT being the only private institution in this elite group. Our objective is to advance the application of mathematics and computational science to engineering, industry, science, and society. And rest assured, math isn't all we do. We are a technical chapter and we like to dive into various domains like AI, ML, web dev, app dev, etc., and aim to find technical solutions to real world problems. Also, apart from this, I want to give big ups to my mentor and senior Shubham Bhaiya, who gave us this opportunity and guided us all along. Also, I'd like to cut you here for the prerequisites. So for this, you just need some basic knowledge about Python and some of its libraries such as NumPy, Panda, Matplotlib, Seaborn, Scikit, etc. But if you don't know what that is, you might want to see the previous sessions of this series. I'll drop the links in the description, of course. But if you straight away want to dive into the core of machine learning, just know that I'll be covering just the required part of whatever libraries we're going to use in the examples that we're going to take. So without any further ado now, let's get started. Although you might already know what machine learning is, I still wanted to give you some examples and explanations if in case anyone's new to this. Okay, so what exactly is machine learning? Actually, we all use machine learning every day without even knowing it. It is basically that field of technology where you make the machine learn to do something henceforth. This is exactly what the tech giants use today in their applications. So for example, I say Google suggestions. Whenever you type something in Google, the ML model knows where you're going to, what you're up to. It predicts some suggestions in the drop down box below, and these predictions that you see are based on some calculations. For instance, your recommendations, your likes and dislikes, or what your previous searches are, maybe what's trending all along in your country or the place you live in. Everything has an impact upon this. It's really precise and it's awesome. Alright, so face recognition. Every time you use a filter or tag your friends on Facebook, the application scans the photograph or the lens and check if the pixels connect together to make a face. If it's a face, then it runs the associated filter code, or it suggests which FB friend this photo might be of. Right? So it has a machine learning model going in background. Or whenever you get a mail in your inbox, your mailing platform understands the mail content, recognize the sender of the mail, and try to classify this as spam or not, whether this mail is really important to you or is it just a spam. Right? Handwriting recognition is, I'm sure, it's known to you in some sort of way, be it gestures or on your phone or this shortcuts or maybe some image scanning for text output, etc. Or I can actually show you this technology right here right now with my stylus pen. All right, so let's see how we can do this. I'm just gonna search something by writing it. Right, so for example, I write, let's say anything. For example, I love machine learning. Right, machine learning. So you actually saw that it understood how I write, and because I write with my stylus pen on my screen, it understood what I'm getting up to, and that's how it gave me some suggestions and results of what I'm trying to reach. Well, you got the point. And there was one more thing that PowerPoint shows you. Alright, so if I go to this draw section and then I click the ink to math section, you can see I can actually write math in here. So let's say, for example, I write sigma of I, there's I from 0, it goes up to n, and there might be a function in it, or I can also add some integral values into it. right? So for example, this works really precisely because I don't need to add these mathematical inputs by searching them online or something. I can actually write them here and it automatically understands what is it, and I can then insert it with this function right here. All right, so let's get back to where we were. Yep, so NLP is the next topic, which stands for natural language processing, and this technology is what Alexa, Siri, Cortana, and Google Assistant uses. It's code run for conversion of text to speech, or maybe speech to text, or understanding the meaning of any speech input. All right, so it's all about that. Data mining is a field of analysis of big data and predicting or interpreting new information from it. All right, and then next, what is it? Amazon and Netflix recommendations are more like Google suggestions, but I really wanted to mention it so to gain a bit of interest of you right there. So, yeah. What are we going to cover? Although there are a lot of topics in machine learning, like regressions, classifications, clustering, or CNN, NLP, etc. What I'm going to start with is the basics, and we'll be covering just the regressions and classifications for a couple of sessions. Alright, so let's start with simple linear regression. And if you got bored even for a second before this, then that time is over. Things are going to get lot more interesting from now, right? So regression is a type of supervised learning. What do we mean by that? What we mean is that we're going to train our model, a machine learning model, by giving some certain values and the corresponding right answers for them. We predict the real values for the given problem. And let's understand this with an example. So suppose I got this data set of housing prices of an area in Portland. I hope this is an actual data set though, it seems like. So never mind. For every value of x in the x-axis for let's say this size, we have the right value along the axis of price. Alright, so if I say that my house is, for example, 1000 square feet large, I got this coordinate here which tells me that my house was sold for maybe $170k, right? So this is an actual data set which is collection of the data that has been recorded in an experiment. What your machine learning model does is it fits a line through this data, right? And then by this line we predict values like this. Like in this case, for example, if I say I want to sell my house that is of 1100 square feet, for example, that'd be for this much price. That is, let's take $220,000 approximately, right? 1 second. Yeah. But how does your model knows where to fit the line? How does it do that? Well, you gotta see this. So this equation right here is the base of all this. This is called the hypothesis equation. And you can recall this as y is equal to mx plus c, where this is the same as that except for the m and c values being theta 1 and theta naught here. Alright, so the equation with these unknown parameters here is arbitrary for now. And to get a precise predicting line like we have here as our black line through the data, we have to find the appropriate values of theta 1 and theta naught. Alright, yes, that's it. That's all you gotta do to find that line, of course. But how to do that? Question is this. You see these gaps here? These little gaps here? Between the real answer and the predicting answer. Our aim is to determine those thetas for which these gaps, or let's say the total distance covering all of these gaps, is minimum. Alright, that's what we gotta do. So, but again, how to do that? This equation, this function helps you out. It's the cost function j that runs over theta naught and theta 1, and we just have to minimize this j function. And as you can see, there's this squared gap in this formula, this one. So this difference, it gets negative. It can get negative in some cases, so that's why we have the square here. Like for example, if we take this particular case, we actually have to do prediction minus the real value. So prediction minus the real value will get us a negative value, and here the prediction minus the real value will give a positive value. So what happens if we not take the square part in it? We actually are going to cross out these terms while we add up these distances, but we are not going to do that. Our main aim is to minimize these gaps. So it's not about the positive or negative signs, it's about the distances that we have. So we're going to take the squares of it so that every value will get positive support, and then we're going to take the average of all these distances, the square distances. But one question more can be arise in your mind, that why do we have this particular 2 here, this one? Why do we have it? Well, it's just for a mathematical purpose, it's for mathematical ease. And where does it benefits us? You're going to see in a short while. Just keep this in your head that this 2 is right here, and you will understand it just in a minute or something. Coming back to the minimizing part, there is this method called gradient descent used to calculate the minimum value of j, and hence the values of theta naught and theta 1, for which the j is minimum, of course. Alright, so how does it work? We got here a plot of j versus theta naught versus theta 1, where j has got different values on the basis of theta naught and theta 1. And now that we initially don't know where the minimum is, okay, we initialize both parameters at a certain place like this, right? And let's take this step up, because see, you have to understand this point that we don't actually know where the minimum is in the first spot. By looking at this curve, by looking at the surface, we can actually tell, like, hey dude, come on, minimum is there. Why cannot you tell that? Because your model does not make these graphs, all right? It makes the predictions upon the basis of an algorithm, and it does not make a graph of this surface and then tells, okay, this minimum is here, so let's take this spot. No, we do not know this graph before, and this graph is just for your visual understanding and for just getting to the real point. What is it? Alright, so this is the gradient descent algorithm that we're going to use. Alright, and we take this function j, then we partially differentiate it, we multiply another factor in it, and then subtract this from the older j right here to get a newer theta right here. Alright, and then we reassign it. So this function, the colon and equal to, you can take this as a reassignment operation. All right, but wait, what's going on? What this is differential? Where did this come from, or where did this alpha come from? We'll look at it one by one. All right, this differential is the gradient with respect to a particular variable that's gonna give me the slope of this j at a particular spot. And what we do this differentiation and reassignment simultaneously for every variable used. For example, in this case, we're going to take these 2 variables, so we differentiate this term to get this term right here, and then we reassign it simultaneously, these 2 variables that we're going to predict. All right, so by the slope, by the help of the slope, we go down the path to the minimum. So from here we go down to here. If this slope is positive, so for example we are at this particular spot, if the slope is positive, then theta j is going to get reduced. All right, so if this spot is positive, like for example we are at this spot and then the slope is positive, this theta is going to reduce. It's going to go in this direction, it's going to go down, because we are subtracting something from a positive value. All right, but if this slope is negative, then this term is going to add up. So from this place we're going to get up at this place, right? So value is going to increase. So what about the alpha value? What does this suggest? This is actually the measure of how long you take the steps. Okay, if the alpha is small, it takes small steps to get down here, and the algo and in that case, actually the algorithm goes slow, right? If you're going to take these small steps, these small steps right here, the algorithm becomes quite slow. But if you're thinking about taking a big step, like bigger steps than that, this step right here, this step right here, then it might get the case that we overshoot this minimum. Actually, it might get the case. So bigger steps are actually more drastic because they never converge your algorithm. All right, it keeps going on, but small steps makes your algorithm a bit slow. So what you have to do is you have to take an optimum value of this alpha, and then you have to make your algorithm work. But well, one more thing is to be kept in mind here, that you might think, this alpha, how are we going to take it? How are we going to know? Well, we are going to code this in Python with the help of a library called scikit, right? So scikit-learn has amazing libraries for machine learning models, and you'll be using them all along. These libraries are, it cross validates your training set on the data on which you train your model, and all of these calculations, the ones that you have no control over it, like for example alpha, they actually give you an alpha without even letting you know, right? So it fits the best alpha, it calculates it with the numerous calculation, and it give it to you without any problem. So one more thing that in these equations I wanted to show you is that I told you to keep in mind one thing before in the former slide. What was it? If you guessed it right, then congratulations. See, we do not have the extra 2 factor in the denominator. Where did it go now? So actually when we differentiated it, the power of 2, which was here in the brackets before, it got down to the numerator, and then it got divided by the denominator term. All right, so therefore we do not have a factor of 2, and that's why we have a bit more solved equation. All right, that than we were going to have. We just have these variables that we're going to take, so that's pretty cool. One more thing that you might think of is, how can we straight away add these 2's in here? Like for example, if we go back here, dividing this j function by 2 without any mathematical proof can be drastic. You might think of that, but it actually doesn't affect the values of theta 1 and theta naught. All right, it is indeed going to affect this j value right here, but the values for which theta naught and theta 1 has, on which j function is minimum, the values of theta 1 and theta naught are going to be same, for which the j by 2 value is going to be minimum. If it doesn't make sense to you, I'll show you with the help of this graph. If the j function is again multiplied by 2, then it might have the amplitude going up. All right, so it might look like this or like this or something like this. All right, then in that case j value might go up, but the values for which theta naught and theta 1, right here, theta 1 and theta naught, these values are going to be same, because this point is just going to lift up. All right, so there is no effect on theta naught and theta 1 in this case. What is this? This is actually an interpretation of linear regression for the question we're going to have. All right, this interpretation here is because of the fact that this graph right here has 2 local minimums, this one here and this one here. So it might be the case that you might start your parameters here, you might initialize them, and instead of going to this place, it might end up here. What then? We won't get the correct values of theta naught and theta 1, so what happens is our line, if it were supposed to go in this direction, it would go in this direction. So that's not accurate, all right? But thankfully, what the linear regression problems are, it's of this type. So we're not actually going to have two minimal spots, we're just going to have one minimum spot. So if you initialize here, 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 or here, it actually doesn't make any difference, it's going to get down. And if you by chance initialized at the minimum spot, then your code is already done, you don't have to care about anything. So now that we have completed the conceptual part, I'm going to give you a short recap of what we've covered, all right? So we just have to predict a y value for every x value. We're going to do that with this, all right, by fitting a line through the data. How are we going to do that? We're going to find the parameters for the line, that is theta naught and theta 1. How are we going to do this? We're going to do this by decreasing the gaps which we had for the real value and the predicting value, right? So we decrease this gap. We're going to decrease this gap by the cost function j, by minimizing the cost function j, and we're going to minimize this cost function j by the gradient descent algorithm. From this we get the correct values of theta naught and theta 1, and then by this fit it in the line, and by this line then we have our value of y for every x. All right, so I'm just gonna discard all this to let you know, and we're going to now go up to the coding part. All right, so I'm going to use Spider for coding, but you can always use Jupyter notebooks as in the previous session that were used. So I'm going to open Spider for now, and by the time it opens, I'm going to tell you where do you get your data sets. So for that, I'm going to open my Chrome, and for solving machine learning problems or for learning it, we're going to get some dataset values. So I'm going to suggest you this site called superdatascience.com, superdatascience.com/machine learning. All right, let's see. Yeah, so this page opens with the datasets which you might require for your machine learning practice. We're solving regressions right now, so we're going to get material for regression. This got downloaded. Let's open it in the download section. Just a second while I go up to here, and then I'll copy, and then in this webinar I'm going to paste it. Alright, so in this folder I'm going to extract this zip file, which is not big, of course, and we're not going to need this now, so I want to delete this. And we're solving simple linear regression, so I'm going to cut paste it right here. And one thing that is absolutely cool about this is they have the dataset along with the correct solution for this dataset in both the formats, that is the Python script format and the Jupyter notebook format. Alright, so that's pretty cool that we've seen it. For now, I'm gonna make this file in my Python. What does it say? Alright, whatever, we'll see it later. So this is the Spider interface. This right here is your script writer, where you write your script and then execute it. This is the console where it directly executes the code. It's the IPython console, which you can actually call it like the upgraded version of Python. And this is the viewer where you can see your variables that you've created, or the documentations which you might require at some times, or the plots that you've created, or the files. Right, so the first step for creating any model is to create a working directory, all right, where you have your data set saved. So I'm gonna open this browser box right here to select my working directory, which I have in SIAM webinar. And in this folder, in the Python section, I have this folder where I saved my data set. Right, so I'm going to select this, and now I can see all those files which were in the folder. So there is the salary data.csv file. CSV is comma separated variables, so these files are actually very popular in cases of data sets. You're going to save your file in this folder, right? So I'm going to make a new file. This new file is we're going to take and we're going to save it in this folder. All right, so I'm going to click save, and in this folder I'm going to save it with practice.py. all right, so now that we've saved it with the CSV file in it, now we can actually work upon our code. So the first thing that you have to do is you have to import the libraries. All right, so we're going to import 3 libraries in it that are NumPy, Matplotlib, and Pandas. All right, so I'm gonna write the code for it, or I have this code written in it. I'm just gonna take this away, the first initial phase of our code, and then I'm going to close it. Alright, so this particular section we have got it done, and these libraries we're going to execute first. We are getting these libraries imported in our console. How to do that? There is a shortcut key in for Windows. It's function 9 key, so I'm going to press function key plus F9, so it executes my libraries in it, and now we have our libraries imported. The next step is we are actually importing the data set. Right, so importing the data set, and let's save our file with the name of dataset. We're going to create a variable dataset, pd.readcsv. This is a function of reading a CSV file. All right, and one more thing cool about this Spider IDE is you can see that, I'm just going to show you in a minute. You can actually see the documentations of it when you're writing the code. All right, CSV. Yeah, click anywhere in this tooltip for additional help, and in the help section you'll get the documentation of this, how to use this function. All right, so there are a lot of functions that you might not remember afterwards, but you can see in this help box for getting these values, what we are going to get, or what we are going to input in this function. All right, so read underscore CSV, I'm going to write my file's name in it, salary.data.csv, and I'm just gonna make 2 variables. One is gonna be x matrix, that is the independent variable matrix, which is going to be dataset.iloc and some part of it, and then we're going to take the values of it. Alright, so let's first implement this so that we can see what dataset we have. I'm going to press Fn and F9. In Windows it's function 9 key, but if you're using a Mac, then you have to press Command and Control plus Enter to execute the selected part of the code. So now that we have this executed, the read underscore CSV function, we can actually see our data set, which is of the type data frame, in the variable explorer. So I'm going to just open it, and we can actually see that we have this question right here. What is it? We have the data set of years of experience versus salary. If I have some experience in my career, for example, if I have the experience of 5.1 years, then my salary is going to is this in an office. So this is an actual data set. We have real values for every x, and then what happens if someone new come to the office and say, well, I have the experience of 6.1 years, what salary are you going to give me? So according to this data, we're going to predict what salary might be like oh, wait a second, I'm just going to show you this particular code by the time. Let's first implement our x matrix right here. As I wrote this code here, and now I'm going to show you what I mean by this code. So x matrix is going to be the independent variable matrix, but salary here is the dependent variable. It's dependent on the years of experience column. So I'm going to get the years of experience column in this x matrix, and then I'll leave the salary part for the y matrix, which is the dependent variable. Alright, so y equals to data set dot iloc. If you don't know what the syntax is, let me just brief you about it. The syntax is, yeah, this particular section is the row section. What rows I'm going to give in to the x matrix. Alright, this section is for rows. As I'm not specifying anything with just the colon in it, it is going to take all the rows we have in the data set. Alright, we're not going to ignore any row. And for the column section, I have this. For the initial part, for the left hand side of this left hand side of the colon, we have nothing. So we're actually telling the interpreter that we're selecting from the initial part of the columns, right, from the 0th column, and then the last value is going to be ignored, so that we are taking just all of the columns except the last column, that is -1. And we're having this -1 without the colon in the y matrix. That means that we're just taking the -1, right? We're starting off with the -1 and not going anywhere, so that means that we're just taking the -1. Right, we don't have any colon here like this, we don't have it. So I'm going to implement this code right here, function 9 key to implement it. And now we have these matrices that we were supposing to have. This is the independent variable matrix, and this is the dependent variable matrix. Alright, we actually separated this so that we can make the distinguish between dependent and independent variables. Alright, so yeah, now the step comes of splitting the data set, this data set that we have, into training or testing data sets. So what does I mean by that? What do I mean by that? I'll better be type this code right here, splitting the data set into training set and test set. Alright, so this particular part of the code is for splitting the data set into training and testing the data set. You can take it as if we have an exam after 3 days, and we got 3 question banks from where we have to practice and learn our subject. Now what we're going to do is we are actually taking 2 question banks and practicing all the questions from it, in which we can also see the answers of all the questions to learn and to prepare ourselves. But we're keeping the last question bank for testing ourselves, that how much that we have learned. Right, so what if we do not split the data set? Actually, if we do not split the data set between training and testing sets, then we won't be able to test our model. All right, how well does it work? we are going to make a small test for it so that we can actually see the differences between how well does it work. All right, we're going to see that. So for this particular part of the code, we are going to take a library from scikit-learn, which I told you about. Right, scikit-learn is just amazing for machine learning models. So here we go. We're taking from sklearn dot model selection import train test split. This is the function that we're going to use, and this is the syntax that you have to maintain while writing this code. Xtrain comma x test, these are the names of my matrices of I'm going to actually split this X matrix here and the Y matrix here into two parts. So we are actually going to have four different matrices with us: Y train and Y test. So you're going to remember this like first there was X and then there was Y. First there was train and then it was test. So these matrices are assigned as the function train test split. See, this spider is actually going to tell you what things you're going to put it. So in the arrays place, you're going to write X, and then after the comma you're going to write Y. Then you have to specify the test size of it. So test size is going to be equal to, let's say, 1 by 3. Why do we take 1 by 3? You can take anything, but the example that I showed you, in which I told you about the question banks, we had 3 question banks and we are preserving this 1/3 of the whole data set, that is the third question bank, for further use for testing purposes. Alright, so test size is going to be 1 by 3. Let me add a bit of spacing so it might get more clear. Now there is one more attribute called the random state. Alright, so random state, let's say I take is 6. What is this random state? Random state is actually used to get similar values of matrices. For example, if you take random state to be 0, your matrices are going to be maintained and it's going to be shuffled in some different order. And if I take as 6 or 4 or 7 or anything, any number else, then it's not going to be in the same order. It's just that's it. If you are going to take the 6 number here in the random state attribute, you're going to get exactly the same matrices that I'm going to get in this particular portion. Right, so let's implement it. Let's say Fn and F9. Yeah, so we've successfully made our training and testing matrices. Let's have a look of them. I'm going to actually close these data sets which were in this portion. Alright, so this is the train part, this is the test part, this is the Y test, this is the Y train. Alright, so as you can see, it has 20 values in it, and the Y train should also have 20 values, the corresponding values of it, and this test is going to have 10 values of it. So it's the last question bank that is the third question bank that has 10 values, and we're going to answer all of this, and because on the basis of this particular column we're going to answer this particular column, and then the predictions that we're going to make, we are actually comparing them with the Y test. Alright, so you'll get to know what I'm talking about. Let's close this for instance, and now is the time so that we can actually train our model. Alright, so I'm going to add this comment like training the simple linear regression model on the training set. All right. So from again from sklearn dot linear model, this is a library used for linear model, we're going to import a class called linear regression. All right, and we're going to make an object of this linear class. Let's say regressor is going to be the object for this linear regression class. Right, so as I told you about, you're not going to actually see that alpha values or the j value function. It just was the concept. You won't get to choose which alpha you're going to take, and it was just the conceptual knowledge that I gave you. These models that scikit-learn has prepared, these models, they automatically tests and cross-validate among, and then they give the right value to you. So it automatically optimizes the alpha value or other values that it has to choose, and it gives you the right answer. So now we have created in this particular section an object of the linear regression class, and now we're going to fit this object, fit all the functions and the algorithm and functionalities of the linear regression class to our training set. All right, we're going to fit this model to our training set, and then this model is going to help us predict the values of the test set. All right, so for fitting, this particular thing is for fitting. Let's say, what if I wanted to show you what is it. So click anywhere this tooltip. This fit has these parameters, and this is its returns. All right, so this just was just an example so that you might get to know what things you can do with Spider interface, or how can you get help or documentations of the different functions. So regressor.fit gives you the help to, let me just write this code first. Yeah, so xtrain and ytrain, we're going to specify this as the arguments of this function, and .fit is going to fit the regressor object of this linear regression class, so that we have prepared our we got our model prepared. All right, so now let's implement this. We've successfully implemented. We got an output of this particular code section. Yes, we have created this regressor, and these are some values that you wouldn't want to know what they are, so just leave this. And now we got our model ready. We just have to predict some values on the basis of our last question bank. All right, so let's say we have this particular code section, which I'm going to call predicting the test set results. All right, predicting test set results. Ypred equals to regressor dot predict. So this predict is also a function, and if you wanted to see what this is, predict is a function which takes the x test matrix. On the basis of this test matrix is going to prepare a matrix of Ypred, and then we can compare this Ypred with our actual y test matrix. All right, so as to know how well the model has predicted. So I'm going to implement this code right here. F9. We have our Ypred matrix ready. Congratulations, you have made your first prediction very well. So there is our y test. And one more thing that is cool about Spider is you can actually see these colors all along your data frame interface. So these colors actually tell you the temperature of your data, how heavy they are. So for example, I have these red data together. The temperature of this data is somewhat similar. So these values are lower, 33,800, 39,000. It's pretty close. And these values are a bit heavy. So for example, 123,000 and 122,000. So these values are pretty close, and we are having the same colors for every number, so that means that we have the same temperature of our values. So that's pretty awesome about our predictions. All right, we are having approximately almost same predictions as we wanted it to have. So I'm just closing this, and after this prediction section I'm going to show you how to actually visualize this portion of yours. So we're going to write this code for visualizing the training set results, and in this section I will plot a scatter plot of the data x versus y, and then we are going to create a line striking through it, and we're going to then compare it with the test set results. Or there's a better way of doing that, so maybe I'll close this and let's open Jupyter for it. Alright, because we have the files here ready for us, so why not we have Jupyter to, let's say, make us see what the visualizing is all about. Alright, so now we have our Jupyter here with this. So desktop, webinar, simple linear regression, Python, and this particular notebook. So it's again the same code that we had. We trained our data set and splitting and everything the same, predicted our data set, and this is the code for, we can actually use it in the Jupyter notebook, the Spire interface also. And I'm going to close this. I'm actually implementing this code here. You can obviously copy paste this code here and enter. So we can see our plot in this portion. So yeah, this line is actually pretty good. By seeing that, it actually really well implemented the linear regression model into it, and we're impressed by it, of course. These are the two question banks. From these two question banks, our model learned how to solve questions. And now I'm going to show you how the model tested itself on the basis of the third question bank. So for the third question bank, these were the questions, and this was the model that was prepared by the regressor object. All right, so this is the model, and on the basis of that, it helped us predict the values of this. So for example, if I say for this particular coordinate, it suggested the value to be around this particular section, and if it was, let's say, this, well, you can actually be sure that these 1 2 3 4 5 are almost lying on the line, so that's pretty great, right? Our model is totally lying upon these coordinates except for some coordinates here, right? So that's pretty cool that we've created such close predictions. So I'm just gonna close this now. Alright, so now that you have seen how to work with the simple linear regression model, we're going to go to multiple linear regression, the concepts of it, and then its code. Alright, so I'm going to minimize this. I'm going to open my presentation, and let's start multiple linear regression. So we're just having some upgrades in it. Like if we compare this to the simple linear regression, there is just an upgrade of this equation getting down to this equation. So instead of having one variable, now we have n plus 1 parts in this equation, n variables with this constant. Along with this, we are arising a concept of matrix calculation. So our machine learning model is going to actually do is it solves this equation. It calculates these thetas by converting this into a matrix like this. It takes the vector theta 1, theta naught, theta 2, theta 3, and so along it to theta n, and then it takes the transpose of it and multiplies it with the X matrix, so that this matrix multiplication will result in this particular equation, right? And then this is the gradient descent algorithm that was used in just two variables, but now is going to be used for n variables right here. The one thing that I wanted to get your minds on is the x naught value here. All right, so this x naught is a remark that every time this x naught is going to be 1. These are the features that we have in the form of the variables x1, x2, x3. So for example, our housing prices is in the form of h theta of x, that is the predictions. These are the prices of our house, but now we're not having just the size of it. We're not having this case, not just having the property size. We're also having how many number of bedrooms in it, how many number of stories or floors there are in the house, everything. These are the features of the house, and this x naught right here is just the constant 1. It's just used to convert this into the matrix formation and then the operations with theta. Also, this x naught here is also 1. All right, there is this concept of normal equation, which is similar to gradient descent. We were using gradient descent to calculate the minimal of j. All right, this normal equation is not an iterative algorithm. It is just an equation. All right, so for example, I have theta matrix equals to x transpose into x, take the inverse of it, and then multiply x transpose into y. This particular matrix is going to be theta, and these are the values of coefficients of these equation right here. All right, so straight away, without any iterative algorithm, we are going to predict these values of theta naught, theta 1, theta 2, etc. Right, so that's pretty cool. There is this table showing the difference between gradient descent and normal equation, which says that we wanted an alpha for gradient descent, but now we don't need that alpha for normal equation. That's pretty obvious. There is no alpha needed. We're just taking the transpose of a matrix, multiplying with it, taking the inverse, multiplying with the transpose again, and then with the prediction value or the real values, the dependent matrix here. All right, so that's going to give us the theta value, but it has some flaws also. So the flaw is that if n becomes large, n is the number of features of the matrix X, or the number of columns that we're going to have. If it becomes very large, then this process might get really slow. So for example, if we have 3 features, then this process is fine. All right, so we don't have to think much about if features are slow. But if features are going to be somewhat like maybe 100 features or 1,000 features, taking the transpose of it, then multiplying it with the x, and then taking the inverse of the whole and then multiplying it with the x transpose, all of this is going to be really slow in the computational world also. So in that case, gradient descent is going to work well because it actually differentiates it and simultaneously reassigns it. All right, so that's not a big deal for computations. So there's this another concept called a dummy variable concept, but I'm just gonna warn you here that this dummy variable, after being an important thing, it's a trap. All right, so yeah, it seems pretty confusing, but let's look at it. So I have this table of information. This is a table of a company which spends their money in R&D section, and then administration section, and then marketing in this particular state. and then it gets profit of this much amount of money from those states, right? From these departments and the state. So this company wants to know that whether we have some correlations between R&D spend, admin, or marketing, or in which state we are working, so that it might focus more upon that particular section where it gets more profit. All right. So which column does this profit has the more of the impact? All right. This company wants to know. But what's the problem with it? How can we implement machine learning model? Is there even a problem? Why wouldn't we want to use it? So there is this problem where we have this equation right here, but what are we going to do with this column right here? How are we actually going to use this with the numerical variables, numerical data here? If you try to do it, you would understand that you cannot actually do it because you cannot write words into this equation, right? So what you're actually going to do is you're taking this column right here and converting this column, the separate variables of it, into two different columns, like here. All right, so this particular two columns are of New York and California. And then what you'll do is, for respective rows, you're going to assign these values. So for example, in this row, New York is present but California doesn't. So New York is going to be 1 and California is going to be 0. This column, this row, has called California to be equal to 1 and New York be equal to 0 because it has California in it and doesn't have New York. Similarly, for every value, we're going to do this process. And then at the final result, we're not going to take this particular column, okay? We have successfully converted into these two columns right here. So we're not going to take this column, okay? But there is also this concept of dummy variable trap. Underneath this, you have to ignore one column of your dummy variable, all right? You have to ignore this, and let's see why. This is because this fact that if you actually try to implement this particular column into your equation, you're actually being repetitive in some sort of a way. Like for example, d2 plus d1 is always going to be 1, all right? So there is a linear relation between them. So dummy variable 1 plus dummy variable 2 is always going to be 1. So if I add this d2 here, our model is going to be repetitive in terms of this d, all right, because it has a simple linear relation between them. So this d2 I can actually represent as 1 minus d1, all right? So it's repetitive in some terms. And then you can actually think of like these three parts of the equation cannot remain together. You can actually think of like that. Why is it like this? I'm just going to tell you in a minute. So what happens is, if you have this dummy variable right here, the New York one, for example, my first row I'm going to calculate and I have New York as 1. So this b4 is going to be here and this dummy variable is going to be 1. b4 along with these other parts of the equation is going to be some calculative information, and then we'll go on to the next step. Now for the next step, our row is going to be California, for example, and in that case this d1 is going to be 0. So for that case, the responsibility of the California information is going to be upon this b0 right here, because it doesn't have any of the features related to it. So it automatically takes up the responsibility of the lost dummy variable. So you are going to actually have just two of these three these three parts of the equation at a time. So the dummy variable trap is, I hope you now understood, and it actually doesn't affect if you have like, let's say 99 of dummy variables. You have to take 98 of them, so you have to ignore one of it. All right, so if you have 10 dummy variables, then you have to take just 9 of them. So it really doesn't have the impact of the number of features or the number of dummy variables you have. The categorical data that we have here, we are just implementing this into the numeral one. We got a trap here, and then we're solving, then we're finding a solution to get out of this trap. All right, it's just about it. I'm going to discard this, and now I'm actually going to show you the code implementation of this. All right, so I'm going to open my spider, or let's say we'll do one thing. We have a certain shortage of time, so what we'll do is we're going to open the Jupyter notebook for the solution that we already have as the super data science package in it, and then we're going to see what we have, what things we're going to do different than linear regression. So I'll open the desktop, SIAM webinar, regression part, multiple linear regression, Python, and then there we have this Python notebook of it. First, I'm going to show you the CSV file also that we have. So let's open this. All right, so this might be a bit confusing, but let's see. So there is this R&D spend column, the administration column, the marketing, and the state, and then the profit column. So this is the company. The question I told you before, it wanted to see that whether we have some correlations in between and this stuff all along. Now I'm going to show you the code. It has some similarities and it's going to have some differences. So the similarities talking about, we have the libraries that are, obviously we're going to import them. Then we're going to scan the data set. We're going to choose which values we're going to take in the X matrix and which values we're going to take in the Y matrix. Then we have this as our X matrix, which are the independent variable matrix. And then we have this part that is going to be different from what we had in the previous simple linear regression section. So this is the part of encoding the categorical data. Categorical data was the New York, California section, which is this, and now you can see that we have another part that is of Florida. All right, so now we have 3 of them. So we're actually going to take just 2 of them, as I told you before. All right, so here we are, and this is the code for computing the computing and encoding the categorical data. All right, so these 2 classes, column transformer and one hot encoder, are we going to use. And then you can actually see that we have these values 0 0.0, 0 0.01, 1, 0 0.0, 0 0.0. So these are the encoding of categorical data that we were supposed to have. Then this part is similar. We are going to split the data set into the training and test sets, and then we're going to have the training part where we train our model on the basis of our training set. And the similarity in this, that we are actually having the same class that we had before, the linear regression class. All right, so we don't have to change the class of whatever model that we're using. It automatically recognizes that, all right, it's not having just one variable, but it has a lot of variables. So let's say this part is completely the same. All right, and we got an output. We successfully fitted our model, and then we have the test results in it. All right, so these test results are going to be executed with this particular section where we are predicting the X test and getting the predictions in YPRED. All right, and then we're comparing these 2 particular sections that are of ypred and then ytest. All right, so ypred is the column that we've just created by predicting, and ytest we have already had. So this was the third question bank that we used. So these are also pretty much close values, as you're seeing. All right, so that's pretty interesting. The bad part of this is we cannot actually visualize what code we have done, because these are a high dimensional space, as we have a lot of columns here, and we cannot actually make a graph out of it. All right, so I hate to break it to you, but I'm sorry. So I'm closing this, and we're just going to jump off to the polynomial regression part right now. Right, so the polynomial regression, it is actually another part of simple linear the evolution of simple linear regression in some terms. So for example, I have this housing prices prediction problem again, and now without the size of it, I have this frontage and depth part with me. So frontage is this part that is on the front side, and depth is this particular part. All right, so I'll write this as depth. So this is a multivariate equation right now, and we can solve this as a multivariable equation, but we can also say that frontage into depth is going to be the size of our house, and we can solve this with the help of one variable only. All right, but this sometimes become really absurd, because sometimes the data set, the values, the scatter plot of it, are not in the favor of simple linear regression. So if I say I wanted to fit a line through it, it's going to be in this form, which is not totally correct, or maybe I'll say in this direction or anything. So simple linear regression with the line is not actually correct for it. So what I'm going to do is I'm going to take another approach, and I'm going to make the graph like this. So this can be of the quadratic form. All right, so for the quadratic form, it's going to be this, and it might go down after this. So but you don't want your graph to go down as the size is increasing. All right, the prices won't decrease as the size increase. So quadratic might be of a little bit no importance in this case, and then you'll hope that you will get a different model. For example, like this is the cubic model, in which you'll have the degree of 3, but it's overshooting this place. All right, it simply goes up really quick, and it's really absurd to see that how the size is increasing normally, but the prices are overshooting this place. So maybe the third degree is also not that good. So for in this case, we can also choose the polynomial part as this, which is of a square root form. So we can write our equation as theta naught plus theta 1x plus theta 2 of root x. So there is just one variable you can see in this, and we are just taking different degrees of it. Right, so for the size, we are taking size and then plus some different coefficient there, and then it's square, or the size plus some different coefficient and then the square root of this. All right, so by cross validation, you're going to see that your model is going to be different in these different polynomial cases. So it's just because we have this concept, because sometimes simple linear regression is not the best that we have. Sometimes the data set is curved, it's the motion of it, it's different, so we have different cases with it. So this multivariate equation is converted into size, like the different forms of it has. And for example, if I have my x1 as the height, it's the breadth, and it's the length, then we have the multiplication of all them, and we just changed this equation in the form of this. All right, so now that we have ended this particular section, I'm going to again open a Jupyter notebook, to show you the part where you can see the polynomial regression in working. So polynomial regression, Python, and then this. And the question, of course, in the form of salary. So this is the question. This is a different question that we had. This is actually the part where the question says that there is a company running and it has different positions. All right, so this is the position level and then the salary of that position. And by the time a person is working and it gets promoted, all right, so it gets promoted from business analysis to junior consultant, then senior, then manager, then country manager, then regional, and so on. Now what happens is, in this office a guy comes and says that, dude, I want a job and I'm a regional manager and I'm working in this previous company of mine, and just take me in. All right, something like that. It's he has come for an interview. So the company asked him to tell about the previous salary of it so that they can give the next salary that he wants to pursue. So it told he told the company that he was having this particular salary, or let's say he said 1.6 lakhs of the salary, and now the company has to check that whether is this person telling right or wrong, whether to take him or to leave him or anything. So we're going to predict the salary, that if it was working on the 6.5th level, how much salary he's going to make. All right, so again, we're importing the libraries, then the data set. We're going to choose a bit of different data set now, and then we're going to train our regression model. Now we're just having this small data set of 10 different values, so we're not going to actually split it into the training set and the testing set, because it's just a little bit of the model. All right, and we're going to predict something that is not on the basis of the model. We're going to predict the salary of the person having the 6.5th level. All right, so here we're training the polynomial regression model on the whole data set and not on the training data set. All right, so for this we're taking the degree 4. You can actually take degree 2 or degree 3 on the basis of checking that which model works good. This model in this case works better than all of this before, so then they took 4 here. All right, so at the first part they're actually going to see how the linear regression model fits this data. So this was the data, this was the graph of the scatter graph of how the levels change, and according to that how the salary changes. And you can see that the best line also doesn't cover much of the graph. All right, so this line here is the best that the regression can reach. But contrasting from it, the polynomial regression tested in this way. It turned out that it actually fits whole of the data pretty good. All right, so this is completely cool that we're seeing this data in this form. This particular point we're having this data, this graph, as discrete form, and it was having the level of the step level of 1 by default in this particular function. But in the next graph we are actually going to see a smoother graph. That means that we have lowered down the step of our smoothness. So now it is 0.1, then it is 10 times smoother than this function up here. So yeah, this is the truth or bluff section, where the company is going to judge whether this person is saying correct or not, and on the basis of that we're going to predict our value. So absolutely this thing is correct, that linear regression won't give us the correct value, so it gives 3,30,000, which is absolutely wrong. But the polynomial regression turns out that it suggests that the employee is having 1.58 lakhs of the salary. So he told in the interview that he's having the salary of 1.6 lakhs, and now the prediction says that it's 1.58 lakhs. So that's pretty close, and it's suggestible that the employee is telling the truth to the company so that they might take him without any problem. All right. So this is a work ethic that the employee was telling the truth. Plus, he doesn't have a bit of greed in him. All those interpretations are of the emotional level, and the company has made its decision to take this employee in on the basis of polynomial regression, because it turned out that he was actually telling the truth. Right, so that was pretty impressive. Now that we have completed these 3 regressions, there is just one part of this lecture remaining, which is of support vector regression. So let's just dive into what we have here. Support vector regression. So first of all, I want you to know that it might be a bit challenging for you to understand what SVR is and how it works. But we'll indeed see how the support vector machine works for classification though. Alright, so for regression, we are not focusing on it because it's visually hard to see how this works. But for the classification process, it's really cool and it's imaginative to understand it. So we'll see it together and that time in the next session. But for this, we're just going to give you a little bit of information so that you might be aware of what SVR is, right? So I'm again saying that I'm not going into deep part of this lecture, but I'm just going to give you a brief about what is it. So basically, SVR does linear regression in a higher dimension. All right, this actually is the fact that SVR takes linear regression only. So for example, if I tell you this line is created by SVR only, but it's not the fact that we are correcting the errors of it. All right, in the linear regression model, what we were trying to approach, we were correcting the distances between the real and the predicting values, that we were decreasing the errors of it. So in this case, we're not actually decreasing the errors, but we're going about in some different approach. All right, we'll see it. So you can think of SVR as if each data point in the training represent its own dimension. All right, so for in this example, every point has its own dimension. So particularly this point is representable on the graph, so it might be having like 1 or 2 dimensions, that's it. But some data have like many dimensions, like n dimensions towards it. And for that, we're not going to actually take this line, we're going to actually take a hyperplane through it. And this hyperplane is not imaginative, it's just a form of this line, this one-dimensional line into the n-dimensional space. All right, and then it said that training sets represents its own dimension. Then when you evaluate your kernel between a test point and a point in the training set, that results value gives you the coordinates of your test point in that dimension. All right, so what does that mean? Kernel is a form of equation that runs over your training sets. All right, and it predicts the values of, and it helps you to solve the testing sets. All right, so this is a polynomial kernel equation, and this is the most used, that is the Gaussian radial basis equation function, which is the RBF function. All right, so these are some of kernels that you can see, and these equations that they're used by the support vector machines to interpret the data and to calculate the real values for the regression problem. Right, the vector that we get when we evaluate the test points for all points in the training sets, we get a vector k vector, and it is the representation of the test point in the higher dimensional space. Once you have that vector, you can use it to perform a linear regression. Simply, this data set is seen as these margins are covering these data sets. All right, so this epsilon has the responsibility of it to cover this by the margins, and then it creates some potential support vectors which actually judges how the data is implemented, or it calculates these stuff to go about it. You might actually don't know what that is, but we'll see. I'm telling you, we'll see this in the classification section. We'll reinforce this whole lecture of support vector machines in that, and that is going to be a next level of your reinforcement, because it's going to be more interesting and it's going to be more informative. All right, so basically this is all about collecting a training set, choosing a kernel and its parameters, and forming a correlation matrix. And then this correlation matrix is going to be used in this equation, and by this equation we're going to take the inverse of k, and then we're going to solve this for the unknown values that we're going to use. All right, so this was the main part of the algorithm. So now that we've done with this half implemented concepts, now we're going to get again the same question of this truth or bluff part, but with the help of support vector regression. All right, so in the Python we're going to see support vector regression Jupyter notebook. All right, so the same thing again. The libraries, there's just going to be one change. I'm telling you about it. The libraries, the data set, the y. This particular code section is just for the formatting of y. We're reshaping y as this particular vector rather than this, because SVR takes its attributes and its functionalities in the form of this. There is this big difference that is called feature scaling that we're going to do about with this matrix of ours. All right, so this standard scaler is used for this. But what is actually feature scaling? You can take it like the fact that we're having again the housing prices in our consideration, and for this we're having features of, let's say for example, first feature is of number of bedrooms, like for example 3, and then the size of the house, that is 3000 square feet. All right, so 3000 square feet is a large number while 3 is a short number, so they are actually not on the same scale. But for evaluating the SVR model, we have to get this on the same scale. Actually, this is a good practice of getting things on the same scale, but the linear regression model was going to do it automatically. All right, so it's predefined in it that whatever values that you're going to take, you're going to feature scale them, and then you're going to use it. But SVR, this model is not used very oftenly, so it doesn't have this by the default in it. All right, so this feature scaling that we're going to use is we're going to create this object from standard scalar part, and then we're implementing this object, and we're going to fit and transform this matrix of our X matrix, and then we're reassigning this X matrix. And now you can see we have our scaling done with all the values being on the same scale, right? From -2 to +2 or something, or +3, -3 to +3, it's going to be in the form of that. Now the part comes where we train our SVR model on the whole data set. All right, so from sklearn.svm, svm stands for support vector machine, we are going to import SVR. This regressor is the object of the SVR, where we take the kernel as RBF that I told you about. Then we're going to again fit our model of SVR into X and Y, and then we're going to predict a new result. All right, so we're going to for predicting, actually what we have done is we have transformed this into the scaling part. All right, but now we don't want our answer to be in the form of -1.2 or for example 2.64 in the scaled format. we want our answer to be in the original format as it was. So we're going to use this inverse transform, where we are actually predicting our answer of 6.5 level, which was the main question. We're going to predict this. Then we are taking the inverse transform it so that it goes back to the original format in which it was. So scy dot inverse transform gives this array of in which the value comes 1.7 lakhs of the salary. So it is actually pretty good that this person was having 1.7 lakhs of the salary. Then also he told that I was just having 1.6, so that wasn't big. All right, many times people say their salary to be better from that they originally have. So that person is telling the truth and the company was impressed by him. We can interpret this question like this. Then we're going to visualize what SVR has to implement, and this particular portion of the curve, we're not having a smooth curve, so we're just having the by default 1 smoothness, and in this we having 10 times smoother curve, so we're having the smoothness factor as 0.1. So this is the smooth curve that you can see of that is prepared by the SVR model. Right, so you cannot see the support vector machines through it who are actually working and making the potential graphs of it, but you can see the conclusion, the interpretation of it, the data handling of it, and it comes out that SVR is, it's not used very frequently in the regression section, but it's actually pretty cool to see the SVM machines working. All right, so I hope this was informative to you, and if you not understood SVR completely, I assure you that you will get a lot more intuition and a lot more reinforcement in the classification section. So stick with me in this lecture till that date, and if you have any confusions or any doubts, feel free to get down in the comment section below. My team and I are there to answer you and help you out. All right, so thank you.